Hello students, and welcome to section 4.3, Right Angle Trigonometry. The six trigonometric functions will kick off by letting theta be an acute angle of a right triangle, then sine of theta, cosine of theta, and tangent of theta. And if you recall, SOHCAHTOA is a very helpful way that we can remember this, such that the sine of theta is opposite over hypotenuse, so O and H. The cosine of theta is adjacent over hypotenuse, so A over H. And the tangent opposite over adjacent, opposite over adjacent, O and A. Now the cosecant, as we've discussed as well, and you should have seen as well prior to pre-calculus, the cosecant being the reciprocal of sine, so you take this and you just simply flip it such that it's hypotenuse over opposite. Cosine, again, is the reciprocal of secant, so hypotenuse over adjacent. And then tangent and cotangent, those are reciprocals, so adjacent over opposite for cotangent. There are buttons on the calculator to do sine, cosine, and tangent. However, there are not buttons for cosecant, secant, and cotangent. So you do need to understand how these apply first in context, and then from there you can go ahead and manipulate or calculate, for that matter, cosecant, secant, and cotangent functions. And yes, where OPP stands for the length of the opposite side to theta, ADJ is the length of the side adjacent to theta, and HYP, the hypotenuse, of course, the length of the hypotenuse. In our prior discussion, we did take a look at how, when we look at a right triangle, we'll be able to make these connections. As a tip, we are shortening the function notation, that is sin, or sine theta, is really read as such. So you do need to consider that the sine of the angle in parentheses will be denoted as such. Okay, so we're going to take a look at some quick pictures here, of which again are mainly review, not just from Algebra 2 but from geometry. A 45-45-90 right triangle can be drawn, labeling both legs as having a length of 1. Use the Pythagorean theorem to determine that the length of the hypotenuse is the square root of 2. And this leads to the following: the sine of 45, so pick one of these two angles on this 45-45-90 right triangle, which also just so happens to be isosceles. Pick this 45-degree angle, so we have opposite over hypotenuse, 1 over 1 root 2, or root 2. And of course you can rationalize, as we've seen, such that you get root 2 over 2, multiplying numerator and denominator by the square root of 2. The cosine of 45 should be the same, because if again you pick this angle, adjacent, 1 over hypotenuse, 1 root 2, or root 2, same thing, you'll end up with the same fraction, and of course the same simplification by rationalizing, root 2 over 2. Last but not least, the tangent of 45, whichever angle we choose, it really does not matter, because the tangent of this angle, 45, opposite 1 over adjacent 1, is the same as the tangent of that angle, opposite 1 over adjacent 1. So opposite over adjacent, 1 over 1, of course, is simply 1. The Pythagorean theorem is actually visible here quite nicely, such that if you maybe didn't know or were able to come up with a hypotenuse as maybe it was provided, let's say, if it wasn't provided, you could do 1 squared plus 1 squared, so a squared plus b squared, and of course that equals the hypotenuse squared, c squared. You can solve simply by adding, you get 2, and then square rooting. So the hypotenuse can be calculated in advance if you needed to using the Pythagorean theorem, and of course it's the square root of 2. You can also dig back to your geometry days when we did do 45-45 right triangle analysis, and you did know that the legs, of which are the same, the hypotenuse is always the leg times the square root of 2. Now let's take a look at a 30-60-90. Similar aspects will apply in context. These are all the respective ratios given those respective angles. The length of the hypotenuse of such a triangle is twice the length of the shorter leg. Label these with lengths 2 and 1 respectively. Use the Pythagorean theorem to determine that the length of the longer leg is the square root of 3. And this leads to the following. So you've got the sine of 30, which is opposite over hypotenuse, cosine of 30, adjacent over hypotenuse, and the tangent of 30, opposite over adjacent. Now these are simplified given the following depiction kind of visually here and geometrically. So here's your 30-degree angle. Okay, opposite of that is 1, and the adjacent side therefore would be 1√3, and then of course the hypotenuse twice as large as the short leg, simply 1 times 2, which of course is 2. If you do the Pythagorean theorem to prove that out, you can do a squared plus b squared and see if it equals c squared, or 1 squared plus √3 squared. Solving for c, you simply add these up, which of course end up being 4, 1 plus 3, and then you end up taking the square root to get your c, of course, to be 2. Okay, this is an analysis that Geometry and Algebra 2 bared out for you. You can of course then do the analysis back to these three ratios as follows. So opposite over hypotenuse, right? The sine of 30, in other words, is 1/2. The cosine of 30 is √3/2. And then the tangent of 30 is opposite over adjacent, so 1/√3. And if you rationalize by multiplying 1/√3 times √3/√3, you get √3/3. Okay. The sine of 60 is the same as the cosine of 30. The sine of 60, if you think about it here, is just opposite √3 over hypotenuse 2. Similarly, the cosine of 60 should equal the sine of 30. Okay, so if I look at 60 degrees, adjacent here of 1 over hypotenuse again there of 2, so 1/2 simply for the cosine of 60. And then last but not least, the tangent of 60 should simply be opposite here, √3 over adjacent there, 1. So opposite over adjacent, simply √3. Since the 9 values up above are encountered so frequently, we do recommend that you memorize them. All of the ratios, for that matter, for sine, cosine, and tangent, and 30s, 60s, and 90s. Now we haven't dug into 90-degree angle specifically in terms of those 6 trig functions, or just the 3 basic ones, I should say, to start. And yes, we will discuss secant, cosecant, and cotangent, so a total of 6. But 90-degree angles, we haven't really talked quite yet about in terms of their actual sine, cosine, tangent, or the reciprocal ratio values, but we will. For now, we do ask that you memorize what we've done above. Moving on, I'd like to draw your attention to the cofunction relationships. And by virtue of drawing a right triangle that happens to have an angle theta, doesn't have to be specifically known yet, we do know though that if this is a right triangle and this is theta, that the other acute angle must be 90 minus theta, right? Because these two angles must add up to 90. Okay, this is already 90, and the 2 remaining acute angles must of course add to 90 if the 3 in total are to add to 180. So if this angle here is 90 minus theta, what would the sine of 90 minus theta be equal to? Well, the sine of this angle here would be opposite A over hypotenuse C. And as it turns out, the cosine of theta is equal to the same thing. In other words, cosine of theta is adjacent A over hypotenuse C. And that actually makes perfect sense back to when we looked at the sine of 30 equal to the cosine of 60. 30 and 60 are complements, we say, of course, because if you add 30 plus 60, you get 90. So the sine of an angle is equal to the cosine of its complement. Okay, so 90 minus theta, or if you just thought of 90 minus 30, of course, equals 60. You think of that ratio as the same, and that makes sense. These are all the cofunction relationships to identify with. We've already discussed the first one. Sine of 90 minus theta equals cosine of theta. It's also true that the cosine of 90 minus theta is equal to the sine of theta. Tangent has the connection to cotangent in a similar manner. And you can see that again here if we just kind of flip-flop tangent and cotangent in context, as do secant and cosecant, and again cosecant and secant, again flipping the trig functions. Okay, there are trig identities that we need to identify with. Okay, there's 3 stages. First, from the definitions, we have what we call the reciprocal identities. Again, we've already discussed these in a review prior to this, but it is important that we reflect again such that, again, sine of an angle is equal to 1 over cosecant, or if you wanted to just calculate cosecant of theta on its own, you would take 1 over the sine of theta. Similarly, cosine is 1 over secant, and of course secant is 1 over cosine. tangent is 1 over cotangent, and of course cotangent 1 over tangent. You cannot type in, because there isn't a function for cosecant, secant, nor cotangent on the calculator. So if you're calculating cosecant, for example, you must do 1 over sine. Similarly with secant, 1 over cosine, and cotangent, 1 over tangent. Second, also from the definition and the reciprocal identities, we have the quotient identities. So the tangent of theta is sine of theta over cosine of theta. And the reciprocal of tangent, because it's cotangent, well, you just take the reciprocal of sine over cosine, which should simply be cosine over sine. And last, there are Pythagorean identities that we connect back to Pythagorean theorem, of course. Opposites squared, and you can think of it again as a squared in a sense, plus adjacent squared, or b squared, equals c squared, or hypotenuse squared. And if you divide both sides of the equation by the hypotenuse squared, which is very interesting, the Pythagorean identities unfold, the most important of which is this: sine squared theta plus cosine squared theta equals 1. Again, this is like saying a squared plus b squared equals c squared. Okay. Turns out that 1 is a very neat result of using this type of identity or theorem really towards the proof of the identity in context, but it works out exactly in that manner. If you were to divide this equation by cosine squared, sine squared divided by cosine squared is tangent squared. Cosine squared divided by itself is 1, and 1 divided by cosine squared is secant squared. Okay. If we were to divide this Pythagorean identity by sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared, and 1 divided by sine squared is cosecant squared, again relating to the reciprocal identities from up above. So for this first example, we're going to go ahead and dig in. It says if theta is an acute angle such that the cosine of theta is equal to 0.3, and I've denoted off to the side that 0.3 is the same as 3/10. So cosine of theta is equal to 3 over 10. So for the first part, part A, sine of theta, well, we could do an analysis of using the Pythagorean identity. Okay, if we do the Pythagorean identity exactly how it suggests, sine squared theta plus cosine squared theta equals 1, or you can also say sine squared plus cosine squared equals 1 essentially. We already know that the cosine of theta is 3/10, so we can square it. You can't see the square there, but there we go, now you can. Okay, so from there, we're again setting it equal to 1, we're going to solve for sine. You're going to solve for sine in a very similar manner as if, let's say, sine squared theta was like a squared, for example. 3/10 squared. There you have it, 9/100ths. On the other side of the equation, I got a common denominator of 100 because now I'll subtract 9/100ths from both sides to get what? 100 minus 9, and you see there we've got 91 over 100. The square root of both sides ends up with a result as such. The square root of 91 over 10. The square root of 100, of course, ends up being 10. So the sine of theta is just that. Okay, for part B, the tangent of theta, okay, we're going to go ahead and take a look. We do know the sine, and we know the cosine. So the sine of theta, we already got to be the square root of 91 all over 10. And of course, the cosine of theta we started with as 3/10. The 10s divide out, or if you wanted to multiply by the reciprocal, well, the 10s are still going to divide out. And your answer should simply just be the square root of 91 over 3. Now there is a picture off to the right that accompanies this. I do want you to draw the picture for this problem just to practice. In the first quadrant we have theta. Okay, we're going to talk about quadrants and angles in quadrants, but later on more specifically. But in this case, if we draw it in the first quadrant, here's theta. Adjacent here is 3. Hypotenuse, here is 10. We don't know the opposite side to theta. You could theoretically just do Pythagorean theorem to find this side. And if you do that, you'll end up with the following analysis. Okay, and you can see a little bit of part D too as I do this. But go ahead and take a look. You'll end up with 3 squared, of course, plus b squared equals 10 squared, and do the math. You'll end up with the same result. Please take a look and try part D on your own with that respective answer, and then parts C and E as well. And then also please finish up taking a look at the notes, and we'll talk about this at another time.